He's going to be talking about entanglement and quantum field theory.
Okay. Well, I'd like to start by thanking the organizers for inviting me to this school. It seems to be a really awesome school, so I hope you're enjoying it. The plan, well, I'm going to talk about entanglement in quantum field theory. Maybe it's a bit of an outlier in the topics of this TASI, so maybe I should motivate a little bit. The basic idea is to think about quantum field theory from a slightly different point of view. In particular, what we want to focus on are the sort of informational aspects of quantum field theory. So quantum field theory is just a quantum mechanical system, and quantum mechanics is inherently probabilistic, so it's very natural to think about information theory, and there's a whole body of work studying quantum information, and maybe we can use their results in quantum field theory, and that's one basic motivation. So it's a new perspective on quantum field theory. It brings a new perspective. Another reason that people are excited is that it does sync very well with other topics that are not directly related to, are indirectly related to quantum field theory, ADS CFT, for example. It also teaches you a lot about renormalization group flow, quantum gravity. It's important in thinking about black hole entropy and so forth. And then the third reason is money. You might have noticed that quantum information is well funded these days. Actually, that's a terrible reason to be in physics, so forget that. Okay, so all right. So and then the plan, I'll start by giving some introductions to quantum information, some very basic facts about quantum information that we'll use later, and then I'll talk a little bit about sort of the general aspects of general expectations for entanglement, and in particular this quantity entanglement entropy in quantum field theory. And then if I have time, hopefully I'll talk about the C theorem, which is sort of a motivational result, which is a sort of derivation of the entropic C theorem using entanglement entropy. Then the last three topics are really sort of methods. They're just methods. They're just different ways to approach this problem. There's the replica trick, which is quite a general method, but it's quite tricky to work with. There's Rindler space, which gives you very powerful results, but is maybe a little bit special. And then there's sort of algebraic methods, which have been around for a long, long time. So this sometimes goes under the name of algebraic quantum field theory, and perhaps you've heard about that before. And really, it turns out that their ideas and methods are very useful for this problem. They weren't directly interested in some of these problems, but their methods will be useful to us. In particular, the important thing that I'll talk about is modular theory, and this modular is different to the modular transformation of 2D CFTs. I'll just say that straight away, so you don't get confused. So, okay, so that's the plan. Okay, so QI basics. Okay, so let's start right at the beginning. So we're going to think about states in a quantum field theory, in quantum mechanics. So we have a Hilbert space, and then we have an operator on that Hilbert space, density matrix. That operator is positive, it's normalized. And there's two classes of states that we'll be interested in. There's pure states, where rho is just a projector onto a one-dimensional space, or there's mixed states, which is everything else. Now, and observables. Observables are just operators themselves, O, and you can compute expectation values of observables, trace rho O, and I won't make any distinction between a Hermitian or self-adjoint observable and one that's not, you can always decompose an operator into its Hermitian and anti-Hermitian part. So that's no loss of generality here. Okay, and then one way to distinguish these two things, pure states versus mixed states, is to compute an entropy, and this will be important for us. Entropy, in particular a von Neumann entropy, which is just this trace rho log rho. And this has the property that it's positive, so let me just write it out, and vanishes if and only if rho is pure. Okay, so this is some way to detect if rho is pure. Okay, and as I said, quantum mechanics is a probabilistic theory. However, it's quite different to classical information theory, and there's really two new things that arise compared to classical information. The first is that you have Heisenberg uncertainty, so you have operators that don't commute, okay? Observables that don't commute, like these. See. And so that's one, and the other thing you have is entanglement. So entanglement is the very simple idea that if I have a system made of two parts, A and B, then I might not be able to write the wave function on AB always as a product of the wave function on A and the wave function of B. Okay? And so it turns out these are new things that arise, but they're actually related. Okay, so they go hand in hand. So, okay, so let's think about this setup where we have a bipartite system. So that means we have a Hilbert space, a total Hilbert space, which is this tensor product. And we'll start by thinking just about a pure state in this total Hilbert space. So this is psi, and this is just a vector, a pure state. Yeah, so I'll also use the language where I'll call, a state is related to this density matrix, but I'll also just refer to a vector as a state. It's a particular kind of state. It's a pure state. Okay. Now we can consider sort of restricting to HA. So the idea is that we're imagining this is maybe some bath or something, and we can't make measurements here. We can only make measurements here. So we're just going to consider observables that are restricted to HA. Observables OA, tensor 1, and I'll often just write that as OA, so I'll forget the tensor with the 1. And I'll use I'll introduce a funny notation which will be convenient later, which is the idea that O is an element of an algebra. So it's a particular kind of algebra. It's all bounded operators on the Hilbert space HA. Okay, so bounded operators just have a finite norm. So the norm of an operator is just the maximum eigenvalue of OA dagger O. And so if we're just thinking about finite dimensional Hilbert spaces, which basically I will for most of this, then these are just all operators, all matrices on that Hilbert space. It's just all matrices. But I will try to use this sort of algebraic language, and in particular, this is an algebra, so it means that I can take OA, I can take O1, O2, and I can add them, and I can multiply them, and they're all in B of A. Okay. And then with this, I can now take my state and I can compute expectation values. Compute values. So OA is just psi OA tensor 1b psi. And then I can simplify this by writing it as a trace. So I can write OA as a trace on the full Hilbert space of this projector times OA tensor 1b. And this is the total, and I can break the trace into two pieces, trace over A and trace over B. But then I can bring the trace over B inside this unit operator, and so it only acts on psi, and I get this equation. And so this tells me to characterize the expectation values of all possible operators on OA, or operators that live in B of HA. All I need to know is what this operator is, and this is called the reduced density matrix. Matrix. So this is row A, and to get it you apply a partial trace. Okay, so this is kind of basic, and so yeah, so this is how we, and so row A is sort of how we think about the state that's accessible to A, so to A. So if I wanted to ask, calculate anything that A could measure, then all I need to know is row A. Okay. Now, there's sort of an alternative point of view, which is a little bit trivial in this case, which is an alternative point of view, but it would be important in quantum field theory. Alternative. And that's the idea that I can think of just the, I can think of the state, rho psi, the state restricted to A as a linear map. So a linear map from OA, which is in this algebra, to numbers, which is just trace of row A, OA. Okay, so this is a linear functional on the operators. In fact, it's what's called a positive linear functional. So rho psi is a positive linear functional on B of HA. And the positive statement is just the statement that if I feed it a positive operator, so let me call that H plus, then I get out a number which is positive. And I should have said that this is a linear map, so it's a linear map from these operators to numbers, and these numbers are in general complex. Okay, so these are just complex numbers. However, if I feed in a positive operator, H plus is positive, then I should get a positive number. So that's a constraint on rho psi. So from the point of view of just restricting to A, I can either think about the density matrix or I can think about this map. And in fact, they're totally equivalent. In particular, if I take operators OA, IJ in some basis, IJ, then I can use this linear map to extract exactly the density matrix in some basis. Okay. Okay, but it makes it clear that we don't really need rho A. So rho A is just a convenience. And in particular, there will be situations exactly in quantum field theory where there's no such thing as the reduced density matrix. And in fact, there's no such thing as a tensor factorization like this. And in that case, we're just going to rely on these sort of positive linear functionals on these on some algebra. Okay, and we'll have to generalize what we mean by this. Okay. The other thing to say is that, well, yeah. Good. Okay, so now let's go through sort of the most important case. So in quantum mechanics, we can start with this pure state on the total Hilbert space, and then we get a reduced density matrix, and it could be mixed. Right, by the definition that I gave before. And this is exactly the case where you have entanglement. So due to entanglement. And the simplest example is to think about a state like this in a 2-qubit system. one. And you can do the math, and I'm sure you all have at some point. You can compute this reduced density matrix in this case, and you just get 1/2 times the unit operator, like this, on the sort of the A qubit. Okay, so this is what's known as a maximally mixed state. Maximally mixed. Now, this, okay, so this is novel. This idea that you go from a pure state to begin with and then you get a mixed state is really novel to quantum mechanics. And one way to see that is to think about, the state that we begin with, psi, and it's an eigenstate of two operators. The parity bit, which is just a product of the Pauli matrices on A and B, Pauli Z, and then the phase is the Pauli X. And these two you can check commute with each other, right? So you can measure them simultaneously. And in particular, this is an eigenstate with value +1, +1. Right? So that means I can measure this simultaneously, and this state is a definite state of those those observables. However, to do this measurement, I need access to the joint system, joint AB, and so if I restrict myself, so only access to A and to B, but separately, so I have two, say A and B are systems that are very far away from each other, and there's two people making measurements on A and B, but they don't communicate, then I can only make certain measurements on A, and in particular the kinds of measurements that I make are things like this, operators like this, but these operators do not commute with both the phase and the parity bit. So there's no way for me to measure this, both the phase and the parity bit, just with measurements on A and B separately. And so this is a Heisenberg uncertainty principle. These don't commute, so I can't measure this state certainly with these kinds of observables. And so this is the origin of this uncertainty and of this mixed state. On A. Okay. So again, because the signature of entanglement is the fact that the reduced density matrix is mixed, we can now invent a measure of entanglement, which is this entanglement entropy. So let me introduce that. Let me start over. Okay. So entropy. Okay, so again, for a bipartite pure system, so that just means that I start with a pure system on the total, then a measure for entanglement is this entanglement entropy, which is associated to A, which is just the von Neumann entropy of rho A, which I'll just often write S of A. And so if this is 0, then in particular the original state had to be a product state, and there's no entanglement. Okay, so let's consider the general case. So general case. So by that I mean I take just a general pure state on the total, and so I can just sort of write that as a sum over some basis of some matrix CIK times I tensor K B, where omega A and B are just the dimensions of the Hilbert spaces A and B. Okay. So this is just a basis, so I can write this in terms of this matrix C. This matrix need not be square because the dimensions of A need not be the same as the dimension of B, so it's in general a rectangular matrix, but you can always diagonalize any rectangular matrix with a singular value decomposition where I write the following equation. I write that C is U some rectangular diagonal matrix times V. So what do I mean by that? I can just draw it in pictures. So this is just a square matrix. It's unitary, so it has to be square of dimension omega A, and then I have a rectangular matrix that sits in between, and then I have another square matrix, which is V. So this is U, V, D, and D is diagonal. Right, but it's only diagonal, it's rectangular, so it's only diagonal across here. And so you can sort of basically see, the dimension of this is omega B times omega B. And so you can then basically see, I'm not going to go through it in detail, that if I just make a basis rotation on A related to U, and I make a basis rotation on B related to V, so in particular, these are state-dependent basis rotations. They depended on the input state. What I can do is I can diagonalize CIK. And the result is called the Schmidt decomposition. So the result is that psi can be written as so psi can be written, well, and let me make another specialization, which I'm going to call the entries. So I should have also said that the entries in this diagonal matrix are positive. So I'm just going to call them square root of P. system, the original density matrix is separable. But if it's not, then it could be that you get something which is not a positive density matrix. It has negative eigenvalues. And so that's that's where this negativity comes in. It's a measure of those the negativeness of those eigenvalues. Yeah. So there are examples, and you can look them up. But yeah. Very good. Are there any other questions? Okay. Okay. So very good. So now let's let's apply this very quickly to this mutual information. So we now know that relative entropy is in some cases is a mutual information. So let's apply monotonicity to that. So apply to mutual information. So let me just write the statement. If I start with relative entropy ABC comparing to row A tensor row BC, and then I apply the quantum channel, which here is just tracing out C, then I should get something that is smaller. So tracing out C, I just get AB now, and then tracing out C, I get row A tensor row B. So this is just a fact about relative entropies. But now let me interpret it in terms of mutual information. Well, this is the mutual information between A and B, C, and this is the mutual information between A and B. Right, so this is just I MI between A and B, C is bigger than MI between A and B. Okay, and this makes complete sense. The mutual information, the correlations between total correlations between A and B, C have to go down if I remove C, right? So if I have less information with respect to checking correlations, then I have to get less correlations. Okay, so it makes intuitive sense, just like this distinguishability idea. Now this is the statement. This is equivalent to the important statement of strong subadditivity, SSA. So let me write it in that form, because we'll need it in a slightly different form later. So let me just write out what these mutual information are. So the mutual information here is, just writing it out in terms of entropies, is SA plus SBC minus SABC. And this should be bigger than SA plus SB minus SAB. And then I can cancel the SAs here, and then rearrange a little bit, and you get SBC plus SAB should be bigger than or equal to SABC plus SB. And so this is strong subadditivity, maybe in a more familiar form. Let me make one more manipulation. I'm going to call this system, did I get this wrong? Yeah, I got this wrong. This is BC. It was right. Very good. Very good. Yeah, so I want to call this, yeah, right. So I should call this gamma. I know what I did wrong. And I should call this alpha. If I call this alpha and gamma, then this statement becomes S gamma plus S alpha is bigger than, well, what is ABC? It's the union of these two. So it's S of gamma union alpha. And what is B? It's the intersection of these two. So plus S gamma intersection alpha. Okay, and we'll use strong subadditivity in this form to prove the C theorem. And we'll, yeah. Okay, so one final thing about relative entropy, which is which will be important for us as well, is to think about relative entropy. Let me go up here. And thermodynamics. So let's say I have some density matrix rho, and I wanted to compare it to sigma, which is just the thermal state. So I have rho and sigma, which is this Gibbs state. Okay. Then you can write relative entropy in a particularly nice form in this case, rho sigma. Well, let me write it out a little bit more. So trace rho, remember it was trace rho log rho minus trace rho log sigma. That was just the definition. But let me add and subtract trace sigma log sigma. So plus trace sigma log sigma. And you see this is like a von Neumann entropy, and this is like a von Neumann entropy. And in particular, this will be the expectation value, trace of something, of this log of sigma. So log of sigma is just minus beta h minus log z. And so what I can write this relative entropy as is a difference in entanglement entropies, or von Neumann entropies, which I'll just call S. So it's a delta S, right? So in particular, it's a minus delta S, where, right over here, so delta S is just S, the final, if I think of rho as the final, as sigma as the initial, is just the von Neumann entropy of rho minus the von Neumann entropy of sigma. That's these two terms, and then these two terms are just, well, the log cancels out of this expectation value because these are normalized, so I get 1. So I just get this, and this is the Hamiltonian, so this is just plus beta times the change in the energy, right? Because it's the expectation value of the Hamiltonian in these two different states. Delta E is just the expectation value of the Hamiltonian in the state rho minus the expectation value of the Hamiltonian in the state sigma. Okay, and then this sort of equation should look a little bit familiar. What is this? Well, this is up to beta is just the change in the free energy. Okay, so S rel can be written as F rho minus F sigma times beta, where F is this usual form for free energy, Ts minus E. And so we learn that, so the basic fact that relative entropy is positive is the statement that the free energy is minimized by the Gibbs state at that temperature. So any other state has a higher free energy. So that's a familiar statement from thermodynamics. The other thing we can do with this is, we've only used positivity of relative entropy in this statement. What about monotonicity? Well, let's consider sorry.
What's the difference between rho and sigma?
The question was, what's the difference between rho and sigma? And that's probably because I wrote this. So sigma is the Gibbs state, and rho is just any other state. Literally any other state. Yeah. Okay. So now let's think about, are there any other questions? Okay, now let's think about what monotonicity would mean in this context. Yeah, I think I should finish. Okay, so monotonicity let's consider, one of these quantum channels. So let's imagine, we have some system, and maybe it's open, so it's interacting with some bath. And we're thinking about some state of that quantum system. So we have some system, we have rho, and there's some bath, maybe, and there's some interactions. And we're sort of, rho is some excited state. So it's not the thermal state. But let's model this, time evolution of interactions with this bath by a quantum channel. Model of time evolution by a quantum channel. We can debate whether this is a good model or not, but let's do that. And let's also assume that, that n, when applied to the Gibbs state, so now it's a quantum channel that maps density matrices on one Hilbert space to the same density matrices on the same Hilbert space. Let's assume that it takes the Gibbs state and gives back the Gibbs state. Okay, so Gibbs state. In which case, monotonicity, well, if I think of n rho as rho prime, this is the model of my time evolution, then the change in the free energy in the in later times has to decrease because of monotonicity compared to the free energy. But we also know that the free energy for the vacuum is the same as the free energy for the vacuum before and after I apply the quantum channel, which tells me that f rho prime should be less than f rho. So the free energy should be decreasing under this quantum channel. So under this process. And this looks a little bit like the second law of thermodynamics. Of course, we still have to justify, and in particular, it's certainly not always justified, this statement that this is true and that we can model this by a quantum channel. But if we can do that in some way, then we get some statement of the second law of thermodynamics. And just to say where we're going with this, this expression for relative entropy, which looks like a free energy, will come up a lot. For quantum field theory, we can calculate sort of relative entropies in certain situations, and it looks like this. And in particular, we'll find a version of the second law of thermodynamics in that case, but associated to black hole dynamics, which is called the generalized second law. And it's exactly related to this relative entropy and monotonicity of this relative entropy. Okay, so that's where we're going towards the end. But yeah. Okay, let me finish there. Yes?
What's the information contained in the part of the relative entropy that's not symmetric between rho and sigma?
Good question. Yeah, so the question was, what is the information contained in the anti-symmetric part of the relative entropy? So one thing that I didn't say, which is kind of obvious, is that this definition is not symmetric in rho and sigma. And so you could symmetrize it, for example, and people do that, and that's some kind of measure. I don't know the answer to your question, though. I don't really know what the utility of that is. Yeah.
More questions? If not, let's thank Tom again.